All right, welcome back. So in this video, we'll be looking at how to compute powers, which the powers of a number are complex numbers. Okay, so um, here's what a complex power is. So let's see in alpha be complex numbers. Then so z to the alpha. This is a complex power, by the way. Z raised to the complex number alpha. Well, we can use this trick of using the exponential and the logarithm, right? E raised to the ln of the complex number z to the alpha. And this is equal to e raised to the alpha times the natural log of z. Okay? Lowercase ln of z is just your normal logarithm of that complex number, right? So we have to look at various number of solutions for this exponential here. So let's look at an example and how we would compute powers of complex numbers. So here's one example for you. Find root 3 plus I raised to the 2I. So try to pause the video and see if you can come up with an answer. Okay, so let's actually go over it. So by definition, right? So root 3 plus I raised to the 2I is equal to E raised to the 2I times lowercase natural log of root 3 plus I. Okay. So let's look at how to compute this exponent number. So 2I times the natural log of the complex number 3 plus I. Okay, so by definition, this equals to 2I times log base E of the modulus of root 3 plus I, which is square root of root 3 squared plus 1 squared. Okay. And then plus I times the argument. So in this case, root 3 plus 1I. So this would be 2. So the radius is 2 and root 3. And then 1 is here. So this is actually going to be pi over 6 plus 2m pi, which n is an integer. N is some integer. Okay. Yeah, so we'll have 2I times log base E of 4 plus 2. So the square root of 4, so that's 2. And we'll have plus I times I plus 12m pi over 6. And so we would have minus pi times 12m plus 1 over 3 plus I times 2 times log base E of 2. Okay, and then n is just an integer, right? So that's one example of looking at the power of a complex number. Okay. And these are their respective properties, which I left for you as an exercise. So for you to work with. Z raised to the alpha 1 times z raised to the alpha 2 is equals to z to the alpha 1 plus alpha 2. Z raised to the alpha 1 divided by z raised to the alpha 2 is equals to z to the alpha 1 minus alpha 2. And then c, z to the alpha 1 raised to the n power equals to z raised to the n times alpha 1. N is equal to 0 plus or minus 1 plus or minus 2 and so on. N's an integer, right? Now these are not necessarily true for the principal value of a complex number, which I'm going to talk about next. So we know that the for the principal logarithm, right? We had theta being the argument of z being a periodic function, right? So we wanted to figure out the principal logarithm for a complex number. And so we're going to arrive this same mindset of figuring out the principal value of a complex power, right? And so, and by definition, z raised to the alpha is equal to e raised to the capital, e to the alpha times capital natural log of z. Capital natural log of z is the principal logarithm, right? So for example, find the principal value of 1 plus I raised to the 1 minus I. Okay? So pause the video and I want you to look at this example on your own. Okay? Okay, so I assumed you worked on this example. Let's figure out the principal value of this number, right? So 1 plus I raised to the 1 minus I, this equals to e raised to the 1 minus I times the principal logarithm of 1 plus I. And then our job is to compute the exponent number, right? So the exponent number, right? This is equal to, 1 minus I times log base e of root 2. This is 1 plus I, so this will produce the principal angle of pi over 4, right? Pi over 4 radians. Okay, so this would equal to 1 minus I times 1/2 log base e of 2 plus pi over 4 times I. And so this would equal to, if we FOIL all these quantities out, so this would be 1/2 times log base e of 2 plus pi over 4 times I minus 1/2 log base e of 2. So minus pi over 4 I squared, so that's plus pi over 4. So therefore, we have the real part, right? So 1/2 log base e of 2 plus pi over 4 and then the imaginary part, right? So I times pi over 4 minus 1/2 log base e of 2. Okay, so that's how you figure out the principal value of a complex power. Let's look at where a power function is analytic, right? Now, as you recall, the principal logarithm or the principal branch, right? The principal branch of the logarithm is analytic on uh, when theta is in between minus pi and pi. So we're going to incorporate this principal logarithm function into the complex power, right? So the principal, right? So they label this as f1 of z, and this is defined as e to the alpha times the principal logarithm of z, right? Okay, the exponential is analytic everywhere, so especially it's analytic on this set. So a composition of analytic functions is analytic. So we know that this is an analytic function, right? So to compute its derivative, right? So to compute the derivative of z to the alpha, right? If alpha and z are complex numbers, well, we're just going to use the definition of this principal function, right? So e raised to the e to the alpha times capital natural log of z. So by the chain rule, this equals to e to the alpha times capital natural log of z times the derivative of the exponent number, which in this case is just alpha over z, alpha over z. Okay. Uh, just by last class, right? Last video, I'm sorry. So e to the natural log of z, since e and the principal log are inverses, we can rewrite this quantity as z to the alpha, right? And this is just alpha times z to the minus 1 by properties of exponents. And so this equals to alpha times z to the alpha minus 1. So therefore, the derivative of a power on z, okay, whose exponent number alpha is a complex number, well, it's equal to alpha times z to the alpha minus 1, right? Okay. And then it turns out this function is entire, so it's analytic. In the well, I shouldn't say entire, it's analytic, except at the point where the it's at all points where the radius is positive, right? So it's analytic, right? And this is its corresponding derivative, right? So, for example, right? and z equals 1 minus I. Okay? Try work on this example and see what you come up with. Okay, so I assumed you looked at this example. Let's compute the derivative, right? F prime of z, so this equals to 1 plus I times z to the 1 plus I minus 1, right? And so this equals to 1 plus I raised to the z to the I power, right? Okay, and so at 1 minus I, the derivative is equal to 1 plus I times 1 minus I raised to the I power, right? And this equals to 1 plus I times e to the capital, I should say e to the I times the capital natural log of 1 minus I, right? Okay, so this exponent number times capital natural log of 1 minus I, this equals to I times log base e of root 2. 1 minus I would be in the fourth quadrant. So that would be minus I times pi over 4. So this angle right here, this is minus pi over 4. Okay. So we'll have so pi over 4 minus I times base e of 2. Okay. Log base e of 2. So thus 1 plus I times 1 minus I to the I power is equals to 1 plus I times pi over 4 minus I times 1/2 times log base e of 2. Okay, so we will have pi over 4 minus I times 1/2 log base e of 2 plus pi over 4 I, and then we'll have a plus 1/2 log base e of 2. Okay, so this is equal to pi over 4 plus 1/2 times log base e of 2. That's the real component, plus I times the imaginary component, which is pi over 4 minus 1/2 times log base e of 2. Okay, that's how you figure out the derivative at that point. Okay, so this is a short video, so complex powers, not too terribly difficult to work with. So I wrote out some problems for you to check comprehension. So where are they? They're right here. So those are the problems for you to work with. And if you have questions, just let me know. Otherwise, we're going to get into some serious functions. So first off, we're going to look at different trig functions that are defined in the complex numbers, and then hyperbolic trig functions. And then right after that, we'll conclude with looking at inverse trig functions. So stay tuned.